Watch a modern fulfillment center, and you are watching thousands of automated guided vehicles navigating a shared floor at high speed, with millisecond precision. What happens to this perfectly synchronized grid if the central brain issuing those commands suddenly goes dark? For decades, industrial automation relied on a strict master-slave communication protocol. In this setup, only the master device is allowed to initiate a transaction or issue a command. This diagram outlines a standard Modbus network. The hierarchy flows strictly top-down. The host processor sits at the peak, while every single path connection routes directly downward to the subordinate units. Because these slave devices cannot act independently, a failure at the top of the chain is devastating. If the supervisory programmable logic controller, the PLC, goes offline, every connected node instantly loses its instructions. The physical result is a shockwave of paralysis. The entire factory floor grinds to a halt, requiring a complete manual system reset to get moving again. The centralized top-down architecture that made modern automation possible is now its greatest vulnerability. When every decision must pass through a single processor, the entire system is only as resilient as that one connection. But complete hardware failure is only part of the problem. Even when operating perfectly, centralized networks break down at scale due to the physical limits of data transmission. Consider the telemetry loop. Every time an AGV checks its position, that sensor reading has to travel up a physical network cable to a central server, be processed, and return. In high-speed mechatronics, distances matter. A delay of milliseconds means an AGV might occupy a space it shouldn't, resulting in collisions. As you add nodes, you hit the latency bottleneck. The central master pulls every device sequentially. Eventually, this hits a physical wall. Upgrading the central processor's clock speed doesn't fix this. Data still has to obey the speed of light through a cable. You cannot compute your way out of the delay caused by physical distance. The solution requires moving the processing power out of the central PLC and embedding it directly into the hardware of the moving units themselves. To scale continuous collision-free operations, you have to abandon hierarchical control entirely. Intelligence must be driven locally, at the edge. This concept is known as edge computing, and it is the strict hardware prerequisite for building a robotic swarm. Look at how closed-loop control systems used to be built. They required massive centralized panels, hardwired together and constantly monitored by human operators. Modern distributed networks operate entirely differently. Instead of sending raw telemetry away for analysis, data is processed directly at the source, exactly where the machine is operating. This requires specialized local hardware, like these control units and variable frequency inverters. They are self-contained, modular devices mounted directly onto the equipment. Instead of waiting for an external command, complex drive control loops execute directly within the firmware of these units, completely independent of a supervisory PLC. When these independent units are networked together, they use peer-to-peer or P2P architecture. In P2P, every local node has equal rights to offer and consume services without ever requesting permission from a master. By communicating exclusively with directly adjacent nodes, P2P eliminates the round-trip latency bottleneck. By shifting computation to the physical edge, data travel shrinks from kilometers to mere centimeters, and it becomes a network of autonomous agents. But if there is no central traffic controller, how do hundreds of independent agents negotiate right-of-way without crashing into each other? They map the environment using a decentralized mathematical algorithm called distance vector routing. Notice that initially, node A only knows about its immediate neighbor, node B. Through successive exchanges, nodes share routing tables. By counting the hops to distant points, information cascades down the line. A node maps the entire network shape iteratively. When a path is suddenly blocked, the network relies on mechanisms like split horizon to prevent endless loops of outdated routing data. If an AGV encounters a physical obstacle, it doesn't query a server. It updates its internal table and artificially poisons the blocked route by marking the distance to that path as infinity. This poisoned route is instantly passed to its immediate neighbors. This triggers a rolling, sub-millisecond recalculation of pathways that ripples outward through the localized area. True systemic stability isn't achieved by a fragile, omniscient central map. It works because every node knows precisely enough about its immediate surroundings to adapt in real time. Early computer scientists adapted these distributed mechatronic models by observing biological systems. This is the application of heuristics, specifically the artificial bee colony algorithm. It models how individual agents process candidate solutions while navigating a crowded shared space. In this model, an employed bee, our AGV, evaluates its position. If blocked, it generates a new route and shares this data with adjacent neighbors, the onlooker bees, using a probabilistic roulette wheel selection. The neighbors weigh the collision probability. The macro-level result is dynamic self-correction. The swarm simply bends its collective paths around the blocked area. Highly sophisticated global behavior isn't being orchestrated from the top down. It is the spontaneous emergence of simple, localized mathematical rules, executed continuously at the edge. Look again at the fulfillment center, now operating under decentralized swarm principles. If a severe hardware fault occurs and dozens of AGVs and their local network switches suddenly fail simultaneously, the system does not halt. The surrounding local nodes instantly detect the dead zones. They apply split horizon protocols and probabilistic route updates, instantly rerouting traffic like water flowing around rocks in a stream. By combining edge computing firmware with peer-to-peer distance vector routing, the latency bottleneck is permanently bypassed. The single point of failure is gone. Removing the central controller is not a flaw in modern industrial architecture. It is the exact mathematical foundation required to engineer systems that can scale infinitely without collapsing.
Thank you for watching. Keep growing every day with just a bit of knowledge. Like and subscribe for more content and continuous learning.